Hello, my name is Marinos Karalambidis and I work at University College London, UK. This tutorial is on SNMP monitoring and has two parts. In the first part, I will show you how to program management applications to retrieve monitoring information from SNMP agents, and in the second part, I will demonstrate how these applications can be practically used to poll a real SNMP agent. So in this first part, I will briefly introduce the simple network management protocol, the associated application programming interface we will be using, the SNMP management information base, and the SNMP protocol data unit. Then I will show you how a management application can be programmed in Java to retrieve single and multiple instance objects and how to perform periodic polling and averaging. SNMP is an application layer protocol, the initial version of which is defined in RFC 1157. This protocol facilitates the exchange of management information between network devices. Although it can be used to both monitor and configure network equipment, it has been traditionally used for monitoring purposes. The main components of an SNMP managed network are the central manager, the managed devices, and the agents are shown in the lower part of the slide. Management applications run in the manager and communicate with the SNMP agents. The latter are software modules that reside in network devices and are responsible for maintaining local management information. For the SNMP application programming interface, we will be using the one developed by AdventNet. The API provides a set of Java classes that facilitate the communication between the manager and an agent. It implements the core SNMP operations and provides a library of these operations for the user. Two types of this API are available, the low-level and the high-level API. The latter implements a wider range of functions, but for education purposes, the low-level is recommended, which is the one we use here. In the manager-agent communication model shown on the right, the agent maintains a set of managed objects and interfaces with which the manager can interact. The managed objects here represent abstractions of the real resources. The manager sends request messages, for example, get or get next messages, and the agent responds accordingly. SNMP itself does not define what information a managed device or system should offer. This information is defined by the SNMP Management Information Base, or MIB, which is specifically defined in RFC 1213. The SNMP MIB is a virtual information store which has a hierarchical tree structure of objects as shown on the right, each represented by a unique object identifier known as the OID. There are two types of objects, scalar and tabular. Scalar objects define a single object instance, whereas tabular objects define multiple related object instances grouped in tables. The SNMP message format specifies which fields to include in the message and in which order. The message is made of several layers of nested fields as shown on the diagram below. The main fields are the version of the SNMP used, the community field which is used for security purposes, and the protocol data unit, PDU for short. The latter constitutes the body of the SNMP message and has the following fields: the PDU type, which encodes the command to send to the SNMP agent, for example, get or get next, the request ID, which identifies a particular request, the error field that takes an integer to identify a possible error, and the list of variable bindings, which is a sequence of two fields, the object identifier and the associated value of that object. It is worth mentioning that the SNMP messages are encapsulated in UDP packets. To poll an SNMP agent, 6 main steps need to be followed. The first step is to initialize an SNMP API by instantiating and starting a new API. The second step is to create and open an SNMP session with a remote host on which the agent is running, and then build the request PDU. This is done by setting the relevant command and the object identifier. The PDU is subsequently sent to and received from the SNMP agent. The next step is to extract the information from the response PDU, which comes back as an octet string. Finally, the SNMP session is closed and the API is stopped. Based on these steps, we now see with code snippets how single instance objects can be retrieved. These hold scalar values and are usually used as counters. It should be noted that the identifiers of single instance objects end with a .0. First, we create a Java class called SNMP_get, the main method of which takes two arguments of type string. The first is the address of the remote host on which the agent is running, and the second is the identifier of the object we wish to retrieve. As a next step, we create a new instance of the SNMP API class called API in lowercase, and we start the created API by invoking the start method. Then we create a new SNMP session, which is the basic communication class for performing SNMP operations, passing the API object as an argument. Using the setPeerName method of the SNMP session class, we set the address of the remote host. Once this is done, we can open the session to communicate with the SNMP agent by invoking the method open. In the third step, we initially create a new instance of the SNMP PDU class called PDU in lowercase, and we use the setCommand method, which essentially defines the PDU type. In this case, the getRequestConstant is used as an argument. We next create a new object identifier, and we set its value to the one we previously defined in the main method. The addNull method is used to add this object identifier to the variable bindings field of the PDU. In the last line, we send and receive the PDU using the sync_send method of the SNMP session object. The request PDU is the one passed as an argument to the method, whereas the result is the response PDU from the SNMP agent. The response PDU now contains the value field in the variable bindings associated with the MID object we requested, so we need to extract this information. The print varbinds method shown in the first line, which is commented out, will return a string of all variable bindings. In this case, the OID and the associated value would be printed out as a single string. However, we could separate the two. To do that, we first need to create a new instance of the SNMP varbind class called SNMP_var, and we assign to it the first element in the list of variable bindings of the response PDU. In this case, we only have one binding since we only request the value of a single OID, but we could ask for multiple OIDs instead. In the last two lines, we print the OID and the associated value separately using the getObjectID and the getVariable methods respectively. Once we have extracted the required information, the last step is to close the established session and the API thread. Here is a summary of the classes and methods we have used for retrieving single instance objects. From the SNMP API class, we used methods to start and stop an API. We used the SNMP session to open and close the session, to set the remote host, and send and receive a PDU. The SNMP OID to set the object identifier. The SNMP PDU to set the SNMP command, add the object identifier, and get the variable binding. And lastly, the SNMP varbind to get the object identifier and the associated value from the variable binding. Now we will see how to retrieve multiple instance objects, such as tabular objects, for example the TCP connections on a remote host. The difference with the previous exercise is that sometimes we do not know the full identifiers of the instances of an object, so we cannot access them. For this reason, we perform a getNext request instead of a get, which will return the immediately next object relative to the table OID we set as the target. First, we create a Java class called TCP_conmanager, and as in the case of the previous exercise, the main method takes two arguments of type string. The first is the address of the remote host on which the agent is running, and the second is the OID of the table we wish to retrieve. As in the previous exercise, we create new instances of the SNMP API, session, and PDU classes. We open a session with the agent and set the target OID. These steps are not shown here. Next, we create a while loop in which we set the command in the PDU to a getNext request, and we keep sending and receiving the PDU using the sync_send method until we have fetched all the table entries. At each iteration, we retrieve a single table row by using the returned OID as the target OID of a getNext request. We exit the loop if the string equality comparison fails. I will explain how this works in the next slide. Inside the brackets of the if statement, we extract and print the information in the PDU as we did in the previous exercise. Now, this is an example OID of a specific TCP connection. The first part, TCP connection state, is the object name, which if you check the SNMP MIB has an OID of .1, .3, .6, .1, .2, .1, .6, .13, .1. This is the initial table OID we can provide as the target. The second and third parts are the local address and local port of the connection respectively, and the fourth and fifth parts are the remote address and port. Together, these parts make a unique OID for a TCP connection table entry. As mentioned in the previous slide, a key issue is to determine when to exit the loop and stop retrieving objects. To do that, we first get the length of the table OID, which in this case is the OID of the TCP connection state object, and we assign it to the integer OID length. Then we get the first variable binding from the list of bindings in the response PDU. We convert the OID part to a string and assign that to object ID. In the last step, we assign part of the object ID string defined by the OID length as a character count to check ID. This is used to check if the first part of the OID in the response PDU is the same as the one we initially provided as an argument to the program. If this is not the case, it means that we are outside the table and we should stop retrieving objects. To display the result, we first get the other part of the returned OID, which is basically from the local address onwards, and in the second line, we split the string into an array using a dot as a delimiter. We can then print out individual array fields. In the last line, the value part of the variable binding, such as the TCP connection status, can be acquired using the getVariable method. The third and final exercise involves periodic polling and averaging, where the objective is to determine utilization, for example, of some network interfaces. The principles are similar to the first exercise, but instead of a single GET request, here we perform continuous monitoring. This can be achieved with a timer task or by having the monitoring thread put to sleep. In the example of the next slide, we will use the former. To do the averaging, we will be using the uniformly weighted moving average method, which is a popular approach for smoothing out monitored values by disregarding spikes in the data. The resulting average value is based on a monitoring interval and an averaging window size. The Java class for this exercise is called UWMAVG, and the main method at the lower part of the code snippet, in addition to the target OID and the remote host address, takes two integers as arguments: the polling period in seconds, which is basically how often we poll the agent, and the window size, which represents the number of consecutive measurements we use to compute the average. In the constructor of this class, in the upper part of the snippet, we create a new timer object and we schedule a task called the remind task, which is executed at every polling period. This involves sending and receiving the PDU and calculating the average. This concludes the first part of the tutorial. In the second part, I will demonstrate how the management applications described can be used in practice to poll a real SNMP agent. Here are some references that can be useful. The Java code for the three exercises can be found in a tar file on my personal web page. The second link is for the SNMP MIB, And on the third one, you can find the Java classes and methods for the low-level SNMP API used. Thanks for tuning in.